Buongiorno. I won't go into these definitions in detail because the best way for you to learn them is to latch on to examples that are meaningful to you. One thing to note, major cells are very important in these four new language features and language extensions. A major cell of an array are the subarrays of rank r-1 on the leading dimension of the array. So for a vector, it will be the scalars. For a matrix, it will be the rows. For a three-dimensional array, it will be the matrices along the leading axis. And for a scalar, the major cell is itself. And in particular, the tally of an array is the number of major cells. And in the extended IndexOff, it looks for major cells of the left argument. And in the most common case, it will be row find. So as I said, the tally of an array is the number of major cells. So for a vector, it's just the length. And for a matrix, it will be the number of rows. And for a scalar, it's 1. And the fact that the tally of an array is a scalar is quite handy. I won't say very much about the rank operator, except that in the monadic case, if you use enclose the left shoe as the operand function, it clarifies how the rank operator works. The last example on the slide encloses the major cells of Q. We'll be seeing a lot of that function later. And likewise, in the dyadic case, if you use link as the operand function, that clarifies how the rank operator works. By the way, when I generated these examples in an APL session, I had boxing on. Now this is a problem encountered in a tuning project with a client this past July. And the problem is to find the number of occurrences of unique elements of a long integer vector. In this case, integers between 0 and 1,000. So using key, it's easily solved. This is a common pattern in using key. If you preface the argument with the universe, then you get the counts in sorted order. And the other advantage is that you get 0 counts for elements of the universe that do not occur. And since this is a million element vector, chances are every element occurs. So comparing the different solutions, A, B, C, and D's, A uses key and is the fastest one. B is slightly longer and uses a modified index assignment. It's not quite as fast as key, but it should be. C is the best that you can do before key and before modified index assignment. Now D is shorter, but it's not practical because the performance is abysmal. In version 14, monadic question mark or query or row has been extended so that question mark 0 gives you a uniform random number between 0 and 1. So the statisticians in the crowd should be happy about that. Now, if R is a random uniform number between 0 and 1, then the floor of 5 times R should be uniformly distributed between 0 and 5. And in this case, you see that that's true. In this use of the key operator, the left operand The left argument given to the operand function is a unique item, and the right argument, omega, are the data items. Since there are people in the crowd, I know that there are people in the crowd that know such things. This can be useful in testing for randomness, in debugging the primitive query 0. You apply key to get the counts, and then you can apply the Kolmogorov-Smirnov test to test for randomness. As I said before, IndexOff, or IOTA, has been extended to look for major cells in the left argument. So it's a compatible extension, so dyadic IOTA on vector left arguments work as before. But if you give it a matrix left argument, then it looks for rows in the matrix. This is actually a very common idea in the real world, where you have a complicated thing and you assign an ID number to each thing. And so that's one way of looking at what IndexOff now does. And so an ID number, for example, in the real world, in the US it'd be the social security number, and in the UK it'll be the national insurance number. And many questions of identity are more easily solved on an ID number than on the original data. So many identity questions are more easily solved on the result of IndexOff than on the original data. We'll see that later. Now we'll now illustrate the extended IndexOff on an extended example, which we encountered in working with a client this past September. A table is a set of values organized into rows and columns. The rows you can think of the rows as records, and there can be as many records as you like. And there's a fixed number of columns. And for our purposes, we consider the data in the column all have the same shape and the same type. And the extended IndexOff works as is on tables. So you can interpret it as looking for record indices. Now, an inverted table is one where all the data for a column are collected together. So all the names together, sex, country, and age. And of course, if you do the tally of each column, they're the same. And if you apply comma bar each on an inverted table, you get something that looks more like a table. So notice that comma bar ravels major cells. Now, to convert between a table and an inverted table is quite easy. Invert the table, invert, uninverts the table, converts an inverted table into the original table. So here's our friend enclosed rank -1, shown in red. It encloses the major cells. So why would you want to use an inverted table rather than the ordinary table? Well, one is space, because in a table, there's array overhead per element. But in an inverted table, the array overhead is per column. And if you have enough rows, then you see the ratio of space. For this example, it's a factor of 16. And the other advantage of using inverted tables is time. So I've generated a 1,000,000-row table. First column are just the letters A, B, and C, and the second column are random integers between 0 and 100. And then I'm in the timing. I'm picking out a column and then compare column 1 and comparing to 50. And you see that in the inverted table case, it's a factor of 15 faster than the ordinary table case. And for this example, the space is a factor of 40 such factors become important if you have 100 million rows, for example. So how do you do IndexOff on an inverted table or on inverted tables? Well, it can't just be iota, but if you uninvert the tables, then you can just use iota. But quite often, you don't even have enough space to uninvert the table, even if you can afford to spend the time. So we will now derive more efficient computation of IndexOff on compatible inverted tables. The top line is an expression that works. Okay, we just saw before. So the next line just substitutes in the definition of vert into the expression. And the next line is a further substitution. You notice that, as I said before, there's a rank, enclose rank -1 in the expressions. Now, enclose, you can look at it as enclose, and another way of looking at it is that enclose generates a scalar representation. And for purposes of IndexOff, a single integer works just as well as the original data. And the stuff on the bottom illustrates this on column 0. So if you say enclose rank -1 on the data of column 0, you get the nested vectors. But if you do x0 iota x0, you get a bunch of integers. So the point is, for purposes of IndexOff, those integers work just as well as the box data above. And mind you, they're not any integers, they are small range integers, which work particularly well. So if you apply the, instead of doing enclose, you do x iota each x, and then mix, and then transpose, you get an integer matrix of small integers. Likewise, if you do transpose mix x iota each y, you get, again, a matrix of small integers. And to repeat, the stuff on the left and the stuff on the right, for purposes of IndexOff, have the same information. So we have solved it. We have an expression for finding IndexOff on inverted tables, shown in red. So a short defun, shown in red there, we placed a 28-line thread fun at the client's site, and it's already 20% faster. And we propose to make that defun an idiom. Now I claim that this application is enabled by the extension to IndexOff, because you could have done it before using the mat iota idiom. But for my small brain at least, that's too many characters. I get confused by the extra characters. Actually, the client knows about mat iota and in fact uses it in the 28-line defun. But again, for them too, they couldn't see through the noise, and they couldn't get the short expression. Yes?
Are the expressions you're putting up on the screen here going to be part of, on the Dyalog result of this conference?
Yes. Both the slides.
I believe you, but I got to do it.
Yeah. Both the slides and I have a script will be on the Dyalog conference website. As I said, the index, okay, thank you, Andy. As I said, the extended IndexOff makes a better tool of thought. I claim that we need a similar extension for sort. Extended IndexOff, find anything. Extended sort anything. Okay, finally, the primitive performance talk this afternoon will have more examples of using the new language features. Okay, any questions? Paul.
So up until now, I've been laminating together columns.
Yes.
If they're numeric or they're text, you convert the numeric column to some text representation using something or other, and then getting a single large text matrix using matrix iota. So so this is going to be faster than that.
Yeah, factor of 5.
Leaving them separate and not laminating all the keys together.
Yeah, once the idiom is there.
Right.
For that particular case, for the client,
That's what they were doing probably.
No,
something. No?
they weren't doing that, but I was trying to justify making an idiom. And for them, it's a factor of 5, to do what you just described, but underneath the covers in the interpreter.
Great, thanks.
Tony.
The small integer representation being much faster for subsequent lookups.
Yes.
How big, what's the overhead of doing that alpha indexed against alpha to generate the small integer representation to do the lookup? At what point does it become so big that you're better off doing the lookup directly rather than generating the small integer step?
Well, I guess it depends on your alpha. If you have a 30-column character matrix, then it's going to be better to have an integer, whether it's a 4-byte integer or 1-byte integer or 2-byte integers. Right.
So the rule would be the larger, the more rows there are in the table, the better off you are doing the overhead of doing the initial lookup that generates the small byte integers is worth it.
Yes. You can easily do that calculation yourself because you know how many bytes.
You can easily do that calculation yourself. Okay.
No, if it's.
I used to be all Ivy in 3 sports, and now I run out of breath tying my shoes. You can still do that.
No, you can calculate. You know roughly how many bytes each row takes.
Give us some idea of the data set you were working with, how many rows, and for the client that you were working with, so that we know.
The client, in that example, he had something like 200,000 rows. And I think he actually knew to use inverted tables. The inverted table had something like 200 megabytes.
Okay. Have you done any work with even larger data sets? I'm talking about several million or
70
million.
Yeah,
because Dyalog, it appears, has a sweet spot of how much data you can work with. But if you start getting into really large data sets, then
well, I cannot see that inverted table would be any worse than the ordinary table because you have overhead per element. So the more rows you have, the worse you are to not invert.
thanks.
Paul.
My limited knowledge of key, would it be true that with the fastest use of key with a given key is using a left argument of using the left operand of alpha and omega only? Would that be a true statement? That any other function, any other left operand would require more work?
This afternoon, I'll give you a list of all the special cases for key that are recognized. And if you have one which you think should be faster, we can do something about that.
Okay, I think probably we don't have time for more questions in this session. So thank you very much, Roger.